this will be the content of what we're going to talk about in this lecture. Let's start into the simple concept on coherence. The beams are considered incoherent if the relationship between them is random. The phase relation is random. Now, and we would say that they are coherent beams if there is a fixed sort of relationship between the phase of the waves. So there should be some kind of constant phase relationship among the phase of the waves that make up the beam. So in other words, coherence actually describes the correlation between phases of monochromatic radiations. Now, in just to have a little visualization in simple layman's term, we look at a human movement. This is during the last hour, as you can see, everyone is moving in. There's all randomly. There's no fixed relationship among the individual movements, the movement of all the individuals here. Whereas in this case, this is soldiers marching. So you can see that there is a constant phase relationship among the soldiers, right? Okay, that's all. Here, we're going to look into temporal coherence time and spatial coherence length. So how do we define that? So temporal coherence time then is actually the time whereby the wavefronts remain equally spaced, as you can see here. The full line represents the maximum of the wave, whereas the dashed lines represents the minimum. So these are the wavefronts, and over here, this region here, they are equally spaced, so we can actually define a temporal coherence time from here to here. Now, in terms of spatial coherence length, then it would be the distance over which the beam wavefront actually remains flat. That would be perhaps this part, small part here, and also maybe just this part here. That would be another coherence length. Okay. Now, since there are two transverse dimensions, so we can actually define a coherence area. Then, in this case, would be along the plane of the page and perpendicular to the plane of the page or the screen. Now here, to give you a better idea, if you look at this, they're equally spaced and they're flat. So we say there's spatial and temporal coherence. Now let's guess on this. It's equally spaced, but that's not flat. So we have temporal coherence, yes. Spatial coherence, no. Here, not equally spaced, but we have flatness, flat lines here, flat wavefronts. So we have spatial coherence, yes. Temporal coherence, no. Okay, so this was the answer just now, and this is spatial coherence, yes. Temporal, no. Here, not equally spaced, not flat, so they are spatial and temporally incoherent. Now, you will find that the coherence time is a reciprocal of the bandwidth. Now, the bandwidth here that we mean would be the width of the spectrum. So, for example, this is the spectrum that we get from the sun. So this is spectrum. So this is the band of our visible light here is from about 400 to about 750 nanometer. So here the band is quite large, and you'll find that the sunlight is actually temporarily very incoherent because this bandwidth is large. Whereas for a laser, which has a very narrow bandwidth here, okay, then it can have a coherence time that is going to be very long because this bandwidth is very small. We would like to define temporal coherence and line width. Okay, now as we've said before, there's no perfect or ideal monochromatic source. Whatever single bandwidth that they have, there always is a small little spread in that particular wavelength. We can sort of represent, for example, in this case, the light wave emitted by a monochromatic source. So you see, it is a sequence of harmonic waves. Okay, is what we call as wave train. So you have one section here, another section, this continuity here, another section here and here. This sequence of harmonic wave train here would have a certain finite length. In this case, it would have a certain time width of tau 1, tau 2, tau 3, tau 4, and tau 5. Okay, so but we can still characterize it by an average wave train lifetime, which we call the coherence time. So the coherence time here could be related to the coherence length, whereby the length will be equal to the speed multiplied by the coherence time. And from the previous slide, we had the coherence time being reciprocal of the bandwidth, so we can then write as such. So now if we take the differential of, but rather this relation, whereby we know that the frequency is equals to the speed divided by lambda. So the bandwidth then will then be equal to, now this is constant, so we find differential of this, and that will be negative c over lambda squared delta lambda. We can therefore now write the coherence length as approximated to, you bring this over here and you bring this over here, you have c over delta mu, and that will give you the coherence length, right? Therefore, we can then define a certain line width. Line width means the spread in the wavelength, as now from the previous one equation here, we just bring this up here, bring this down there. So we have delta lambda approximated to lambda squared divided by the coherence length. Yeah, as the line width of the spectral source, we can measure that. So then we can then calculate the average coherence time. And then we can also estimate the coherence length. For example, just now we talked about white light, which was from the sunlight. The light width here is about 300 nanometer, and the average wavelength is about 550 nanometer. So with these values here, we substitute in this equation here, then we can calculate the coherence length, which is equals to 550 nanometer squared divided by 300. That gives us 1000 nanometer. Now that will be about 2 times this one. In other words, coherence length is only about 2 of the average wavelength. Now this length is actually very small. So when you do interference of light using white light, it's actually difficult to obtain the fringes, because the difference in the two, phase difference between the two must be within these two wavelengths only, which we will see later when we talk about Michelson interferometer. Now for sodium or mercury gas discharge lamp, they have this discrete line emission, but so we can sort of say they are monochromatic. For example, the green line of mercury at 546 nanometer, it has a line width of about 0.025 nanometer, and that will give us a coherence length of about 1.2 cm. So that's great because there's many wavelengths that can fit into that. Whereas for carbon dioxide laser, for example, it has a line width of only 10 to the minus 5, so short, 10 to the minus 5 nanometer at the IR emission of 10.6 micron. Now, this is beautiful. It gives us a coherence length of about 11 kilometers, actually. Okay, next we look at spatial coherence. Well, spatial coherence is known to depend on the emitter size and its distance away. And what do we mean by this? Now, according to the Van Zernike theorem, it states that the spatial coherence area is given by d squared lambda squared divided by d squared, small d squared here, where small d is actually the diameter of the light source, perhaps diameter of the light source, and d is the distance away. So which means that the spatial coherence area will be larger when you're at a further distance away, right? Or when the small source is very, very small. So in comparison here, this would be very large, right, if this is very small. Now, basically, what we mean here is that when you go far away, even your spherical waves, when you go far away, the spherical waves will then smooth out as they propagate further and further away from the source. So sun is not so far away, but stars are further away. Yeah, starlight is spatially very coherent because stars are really very, very far away. I mentioned about the sun and the star being far away. Well, the star being further away. So here I drew up from the internet a quick one. Distance between sun and earth is about 150 million kilometers. And the nearest star to earth is the Alpha Centauri, which is 4.24 light years away. Uh, 1 light year is about 9.5 million kilometers. So definitely the star is really very, very far away. And here is a map of some of the stars which are even further than Alpha Centauri. Okay, come back to this. Basically, we are on the topic of coherence, and that will bring us to the interference of two waves. So coherent topic here will also relate to interference. So first, let's do the irradiance of sum of two waves. So if we have two waves of the same color, meaning they're monochromatic waves, light waves, then if they are of the same polarization, then the resultant irradiance will be the irradiance of wave 1 and wave 2. And also added to it, we will have an interference term here. This will give rise to that variation of constructive and destructive interference, which is manifested in terms of a bright band and a dark band, which we call interference fringes. Of course, if they are of different polarization, even though they are same color, you then just get the total irradiance equals to a simple sum of the individual irradiance. Likewise, if you have the two waves of different colors, though of same polarization, they are still the same. And of course, with different polarization, different colors, then it's just a simple sum of two. So the only condition where you can get the interference pattern, then that occurs only when the waves have the same polarization and the same color. We said that there would be interference if we have the two waves having the same polarization or they are monochromatic. So here we can have a beam and then combining with a delayed replica of itself. So we'll talk about how to produce that, but being delayed is a replica, so they would have same polarization, same color, and they will produce the fringes. So how do they do that? Let's look at the irradiance, the variation in the intensity. So the resultant of the two waves when they combine will be given by this expression here, whereby this is the interference term. Now suppose the two beams, the first one is denoted by E0 exponential I omega t in complex form, written in complex form, and the other one will be E0 exponential I omega t minus tau. Tau here is that delayed time. So when two of them combine, now look here, we have them having the same irradiance here. So I1 and I2 would then can be replaced by I0. So we add them up, get 2I0. So and then the interference term will be given here. You have C epsilon real part of E0, the first wave, dot product with the complex conjugate of the second wave. So you've added the negative here, there's a conjugate here. And if you look at this, you'll find that this and this cancels, and that leaves us only with the exponential I omega tau. So this one multiplied by this, the conjugate of that, so that will give us squaring of the electric field amplitude here. And taking the real part, then we just have the cosine function, cos omega tau. So C epsilon E0 squared is actually the 2 times the intensity or irradiance of the wave. Yeah. So this is a common factor we bring up. We have 1 plus cosine omega tau. So what does that tell you? Therefore, the resultant irradiance will be consisting of that 2 intensity add on a cosine function here. So it's going to vary maximum, minimum. So this is what we're going to get. This is the intensity and this is tau. So you find that it will have this variation. And how do we introduce that delay? So we can do that on purpose by using a mirror. So this is the input beam and this is a reflected, which is the output beam. So we introduce this time delay by translating this stage that holds the mirror. So by moving a distance of L would result in a delay time of 2L divided by the speed of light, assuming it is in air here. So in other words, if you look at this, we make a quick calculation here. The light travels at 3 micrometer per picosecond. Just another way of putting it, which is 3 times 10 to the power 8 meters per second. So if you translate this mirror by 300 microns, well, the strand of hair is about 200 microns. So you can imagine how small the distance would be. That would give a delay of 2 picoseconds. Okay. Instead of using a single mirror, we can also use a pair of mirrors, but the plane in which they're tilted has to be aligned such that the return beam will be parallel to the input beam direction. Yeah, otherwise we'll have difficulty getting the interference pattern. Now, so this tilting here can be overcome. This problem with the tilting can be overcome if you use what we call corner cubes. Basically, it's a hollow cubes here. These are pictures of some of these glass tubes by Edmund Scientific that shows it being hollowed out in the center. That is to avoid the ray from propagating to the glass, because glass will introduce dispersion. So it only gets reflected at the surface and is still traveling in air. So this will introduce a delay in time. Another example of introducing the delay is the Michelson interferometer. In this case, we have this input beam. It is then divided into two. One that is reflected at the beam splitter, goes along this path and gets reflected and pass through it and come along the output beam. The other one that is transmitted and it gets reflected by this mirror, goes back along those way and gets reflected now by the beam splitter and combined along the same direction. So then we write the equation for the output irradiance. Okay, is contributed by the irradiance of beam 1 and irradiance of beam 2 or wave 2 and plus the interference term. And here we have actually assumed that the input beam is a plane wave. So the irradiance terms will be given by C epsilon, the real part of first part, half part beam and the second half part beam in that sense. Okay, so it will be contributed by E0. We can write E0 exponential I omega t minus kz minus 2kl1. So if we just rotate this along this direction, and because then we can what we call as the equivalent optics. You will learn about this in about 2 or 3, probably about 2 lectures later. And then the complex conjugate of the other portion that will be contributed by E0, assuming that they are equally divided in terms of amplitude. So we have exponential conjugate, complex conjugate, so negative I omega t minus kz. Now in this case it will be minus 2 because it doubles back here, because it's being reflected. So 2kl2. And if you look at this equation, well, this and this cancels. That leaves us with 2k into L2 minus L1. So we have exponential 2ik L2 minus L1. Okay, and here we have replaced I1 and I2 with I, whereby it is equals to the irradiance of the split beam, yeah. And just like previously, taking the real part, that gives us the cosine of k 2 L2 minus L1, whereby we have substitute 2 into L2 minus L1 by delta L. So as you can see, as with the previous slide, you get this variation in irradiance expressed by this. So that's why we will get the dark fringe at the body, and these peaks here will form the bright fringe just by introducing a delay in time. So it's the interference of a beam and the replica of itself with a delayed time, yeah. Now, let's look at this famous experiment, Michelson-Morley experiment. Now, they are the 19th century physicists. At that time, they postulated that there exists a certain substance, a media called ether, because they think that light is a vibration, similar like sound, that needs a medium to travel. So both of them then realized that the Earth could not be stationary with respect to ether. That existence of ether at that time was believed to be so. Well, then if the velocity of Earth is to be along this direction through the medium called ether, then they postulated that if they did this Michelson interferometer here, this beam would be propagating perpendicular to the direction of the supposed velocity of Earth. And here this beam will be parallel and anti-parallel to the velocity direction. Then in that case, light then would then have a different phase shift depending on whether it's propagating this direction or this direction. But from the experiment, no phase shift was observed, so it disproved the existence of ether. Well, interference is easy when the light wave is a monochromatic plane wave. Remember, we say single color. So for a perfect sine wave, the two beams can be either in phase or they're out of phase, right? So what about a beam that has a short coherence time instead? If they have long coherence time, then it's quite easy. For example, let's look at this. Here, we can probably define a certain coherence time equally spaced somewhere here to here, and then you can see they are out of phase here. So in other words, what we're trying to say, at this particular captured moment, there is a certain part here which is out of phase. So in other words, we can say that these two beams then would be in phase some of the time and out of phase some of the time, and they are varying rapidly. So, but in a lot of optical measurements, it's usually measured at a time much longer than the variation, the frequency of the light. So this variation will get averaged out. So then, if we add a non-monochromatic wave to a delayed replica of itself, what will happen? If the delay is 0, constructive interference for all time. If there's no delay, they match perfectly, peak to peak, valley to valley, right? But if there is a delay of half a period, well, we will get destructive interference at the part that matches very precisely. At the part that doesn't match that well, we will have maybe not so dark fringe, but in the part where they are totally out of step, then you get total destructive interference. Now, if this is delayed by half period, which would be much less than the coherence time here, but if the delay is larger than the coherence time, then you will not be able to find any part that will match well, and you won't be able to see the interference pattern, in other words. So it becomes incoherent addition. In order to have interference, coherence is actually important. Talking about non-monochromatic plane waves, so when they interfere, when they're brought together, do we still see the pattern? Well, we can still see the interference fringes if you can define a coherence time, even though it's a short coherence time. As long as you have that time where they are coherent, then we can still get those interference fringes. Now, let's say now we do not have parallel beams, but we have cross beams coming across each other. Just now, Michelson, the output were all parallel, so we get the interference pattern as well. But if we have cross beam, what happens? For example, in this direction and in this direction, we can, this propagation constant or wave number here, we can define z component and an x component. K minus also can define a z component and an x component. And the position vector is given by x plus y, and z, unit vector z here. So the dot product of k positive with r and a k negative with r will give us these two expressions here. We have kz cosine theta plus kx sine theta. Here we will have kz cos theta, okay, and x and x1. So kx minus kx sine theta. There's a minus here. So the resultant irradiance, okay, assuming that the two beams have the same irradiance, so we still have the 2I0. Now here for K positive beam, we write in complex form again, E0 exponential I omega t minus K positive dot R, yeah. Whereas the time delayed one is in this direction, so the complex conjugate here, E0 star here, exponential negative I omega t minus K negative dot with R. Now, if you look at this, just look at this cross term here. It would be proportional to, we can write it as expanding this with this expression and this one with this expression. So we write in this form here. Now, looking at this equation, this one cancels this negative and negative positive. So this and this cancels. This negative kx sine theta. This is also negative kx sine theta. So we will have the real part of now E0 and E0, the conjugate here will give us E0 squared exponential negative 2I kx sine theta. And taking the real part, we will have E0 squared cosine 2kx sine theta. Okay, so the maximum irradiance will occur when 2kx sine theta is equals to 2m pi. That is when x is equals to m pi over k sine theta, right? And the fringe spacing, that means the spacing between consecutive fringe here, would actually be given by 2 pi over 2k sine theta. 2 pi when m, the delta m is equals to 1, I mean from m plus 1 to n. So you find that it will be equal to 2 pi over 2k sine theta, fringe separation. So again, we get this cosine variation. Yeah. Now, if you look at these two beams here, just visualization of it, the green part represents one beam, pink part represents another beam. So at the part where they overlap very well, you get this interference pattern. At the part where they didn't overlap totally, you still get interference pattern, but towards the side where they didn't overlap, you don't get the constructive and destructive interference. And as you move further away, the pattern changes. Yeah. Now, looking at the fringe spacing just now, if the crossed beam angle is large, that is, theta is large, sine theta will be large, fringe spacing will be small because this term will be small. So they are narrower fringes. But when the angle is small, its denominator becomes a smaller number, fringe spacing will be a larger number. So as the angle decreases to 0, basically we have fringes which are more widely spread. Okay, and as the angle decreases 0, the fringe becomes fatter and fatter and fatter, and finally at theta equals to 0, the intensity pattern becomes constant. And you would not be able to see the spatial fringes if the angle is very large, because they'll be so narrow you could hardly see. So if the angle is small, then you see those fringes separated clearly. Now for a fringe separation of 0.1 mm, that will be about the minimum separation that we can see well. So writing this, approximating sine theta to theta, that will be equals to lambda over 2 multiplied by fringe separation. And in other words, that will be equals to, let's say, visible range, we put the middle value, which is 500 nanometer, divided by 2, and fringe separation of 0.1 mm. That will give us 1 over 400 radian, which is about 0.15 degree. Okay, so that would be the minimum fringe spacing that we can see. The angle separation will be larger, so we really need the cross beam angle to be very small. So in fact, the best is still parallel beams. We're talking about spatial fringes and spatial coherence here. Now, what if the beam is temporally coherent? As you can see over here, they are equally spaced, but not spatially coherent. So these fringes are not flat. Do we see fringes? Can we see interference fringes? Well, that depends. If you look at this, this is the direction where the blue beam is coming. This one is the green one. It is coming at a certain very small cross angle. And you would be able to get the interference fringes along the region whereby the same region of the wave interferes, but at a region whereby very different region of the wave interfere, where they over as further away from this region here, then there will be no interference. Now, in the Michelson interferometer that we did earlier, we had aligned the mirrors in such a way that the output beams reflect that came from this mirror, and from this mirror they were parallel and aligned. But now, if those beams comes crossed, what's going to happen? That means, in other words, the mirrors are actually misaligned. We still can get interference pattern, except that we won't scan the delay, because in the aligned condition, the interference term gave us the cosine term, which is k multiplied by 2 times the distance, the difference in the distance that the light travel from the beam splitter to the respective mirrors, delta L, remember? So that was just by translating one of the mirror that would introduce that delay. So we were actually scanning that delay. But and here, if the input beam is still a plane wave, then the cross term now will be similar to the expression that we derived for cross term. And you find that the output irradiance would then be proportional to cosine of 2kx sine theta now. Yeah. So we would still see fringes. Now, these are some example of fringes that you will see depending on the tilt of the mirror, in other words, the alignment of the mirrors, and depending on your view also, that is whether you are at theta equals to 0. If theta equals to 0, that is you're looking right into the bullseye. And here we'll talk about path differences as the difference in the two arms. So if L2 minus L1 is 0, we will see fringes that are parallel, or this or at a position where you are at very near the center, then it sort of flatten out. So it fills up here, the view, it flattens out. As you go further, as the path differences increases, either one is longer than the other, L1 longer than L2, L2 longer than L1. So you'll find that the fringe patterns then gets narrower, and here you start to see the fringes appearing. And as you go even further, they become even more narrow, and over here they're so narrow that you could hardly resolve it. Yeah. Now this is a sample of the Michelson interferogram from white light. Because the coherence length is short, in other words, the spectrum is large, the line is large, so the coherence length becomes very short, which we worked out was about only 2 wavelengths. So as you can see here, there's only about 2 wavelengths here that is black. The rest all are where the component colors give you constructive interference. That's why you see the color bands of that. So only about 2 wavelengths you get fringes of white light. Here is an application of interferometer, but in this case the arrangement is slightly different. It's actually Mach Zehnder, which is a variation of Michelson. We'll talk about this in about 2 or 3 lectures later. And when a plasma is present, for example here, you'll find that because the density is different, so it introduces another set of fringe patterns. So that's one way of imaging the plasma. So, okay, we come to the final learning outcomes. You should be able to define the concept of coherence, temporal coherence time, spatial coherence length. And you should be able to explain relationship between coherence length and line width. We did some derivation there. And you should be able to derive the irradiance of the interference term. And you should be able to describe interference from beams with delayed time differences between them. And you should be able to derive This should be no D here. Interference term for Michelson interferometer and cross beam system as well. And you should be able to describe the dependence of the fringe separation on cross beam angle. Thank you.